Josh Acay from Cornell, and I'll be talking about verifying a compiler that generates cryptographic code. So the thing about distributed applications is they're a pain to write because you have a bunch of mutually distrusting parties. They're communicating over an untrusted network, so you have to manually chop up your application into little pieces and make sure you do that correctly. And on top of that, if you want any sort of security, you probably need to use cryptography. So really, this is what your application looks like. You have a bunch of mutually distrusting parties that are calling into some cryptographic libraries, like a secret multiparty computation library or zero-knowledge proofs. And then the programmer is manually deciding, okay, this piece of code needs to go into secret multiparty computation, and they need to make sure they use the libraries correctly. This is obviously incredibly error-prone. So the idea of our compiler, Viaduct, is just let the compiler worry about cryptography. So the programmer writes a single-threaded sequential source program. They specify their security policy using information flow labels. And the Viaduct compiler basically figures out, basically generates a distributed program for you. It figures out what code needs to live on what host, and it figures out how to call these cryptography libraries correctly. And importantly, there is no mention of crypto in this source program. So we've implemented the Viaduct compiler. This talk is going to be about proving the security of it. But first, I need to tell you how the compiler works in a nutshell. So the entire thing comes down to information flow labels. This is how you specify your security policies. For Viaduct, an information flow label is a tuple of a confidentiality component and an integrity component. Each component is basically a Boolean formula. And means more, or means less. So A and B is more secret than A, and it's more trusted than A. Standard information flow typing stuff, all data has a label attached to it. So if you, for example, input from Alice, that gets a label A, A, because that has Alice's secrecy and integrity. If you combine data from different participants, like if you do A plus B, then you basically increase secrecy because you have secrets from two different parties, and lower integrity because the competition uses data from two different people. So it's fundamentally less trusted than using data from a single party. In Viaduct, hosts also have labels. So simple hosts like Alice's machine and Bob's machine have simple labels that correspond to that person. So Alice's machine has the label A, A. An idea we borrow from the cryptographic literature is we introduce an intermediate step where we model cryptographic protocols as idealized functionalities. So an MPC protocol between Alice and Chuck can be modeled as a host that runs some code. This is very similar to just the Alice host. And these also have labels, and what they give you is a stronger label. So a maliciously secure MPC protocol can give you high confidentiality and integrity, which means it gives you A and C confidentiality and A and C integrity. A zero-knowledge proof protocol, where Bob is the prover, may give you higher integrity because you prove to Dave that the data is correctly computed, but Dave can't actually see the data, so it only gives you Bob's confidentiality. And the main idea basically comes down to data has labels, protocols have labels, combine them. And let's look at that in action. So we start with a source program. This is the classic Millionaire's Game example, where Alice and Bob want to figure out who's richer without revealing their net worth to each other. So the program is pretty simple. We compute Alice's net worth, store it in A. We compute Bob's net worth. We check is A less than B, and then output the result to both parties. There are these endorse and declassify statements. This is basically how you specify the security behavior of your program. And endorse says, I am willing to trust data. So the A is coming from Alice. Normally, Bob wouldn't trust A, but an endorse is saying, I don't care how Alice computed that value, just trust it, take it as is. A declassify is saying, I'm willing to reveal this result to the participants. So obviously, I don't want to reveal A or B, but I'm OK with revealing A less than B, the resulting 1 bit. Next, the compiler analyzes this program and comes up with a label for each statement. So the first statement only uses Alice's data, so it has the label A, A. The next line only uses Bob's data. The third line is the tricky one. So It has A and B confidentiality, which means it has high secrecy. And we figured it out by looking at the inputs of the computation. Because we have inputs from both Alice and Bob, in order to run the statement, we need high confidentiality. For the integrity, we want to look at where the data is going. So because R is output to both Alice and Bob, we want both Alice and Bob to trust the data, so its integrity is A and B. Finally, once we have a label for each statement, we can assign a protocol or a host for each statement. And the constraint here is that the label of the host must be stronger than the label of the variable. So the first line has the label A, comma A, so it's Alice's confidentiality and secrecy. Alice can compute this value locally. Bob can compute the next line locally, but the A less than B computation has high secrecy and integrity, so we must do that on an MPC protocol. And in general, here the labels actually match up exactly, like the labels on the data and the labels on the host match up exactly. This is not necessary. Obviously, you could just do everything on an MPC host, but that's less efficient. Once we have a protocol for each statement, partitioning is actually pretty straightforward. We do it pointwise, so there's a projection function. And basically what you do is you say, okay, I'm trying to figure out what Alice is supposed to run. You go through the program, and for each line, you figure out what Alice needs to do for that line. If you're familiar with choreography programming, this is basically endpoint projection. And as a final step, so we have these idealized hosts. We just modeled MPC as some host that runs some code. We need to implement it using an actual cryptographic library. So we will instantiate this by Alice and Bob running some protocol and calling it to some secure multiparty computation library. All of this stuff so far is prior work. We've implemented the compiler. It supports secure multiparty computation using ABY, zero-knowledge proofs using libsnark, replication commitments. We also have some evaluation and benchmarks. The one thing this paper is missing is a security proof, and that's what I want to talk about now. And this is work in progress. So before we can prove that our compiler is secure, we need to answer this philosophical question of what is correctness? And functional correctness is not enough. So you can't say, oh, the generated program produces the same value as the source program because we want to talk about attackers. You can't say they produce the same values under all attacks because you can generate the same value while leaking way more information. So really, we need a notion of correctness that takes security properties into account. On top of that, whatever proof technique we use, we want it to be extensible and compositional. So Viaduct, the compiler, is extensible in the sense that you can add more backends without rewriting the compiler. And we would like our proof to be, the proof to mirror that. So we don't want to fix a set of cryptographic protocols, or another way of saying it is, I don't want to redo the entire correctness proof every time we add a new backend. Additionally, we want to be able to use proofs that are out there in the literature. So if somebody has implemented an MPC library and have proven it correct, we don't want to redo the proof. We just want to use that proof. So the answer to both of our questions is this framework from crypto literature called Universal Composability Framework. Its main point is basically to give you compositionality. It allows you to describe your protocol at a high level and swap out little pieces with other protocols. So what we're trying to do here is, on the left, I have the generated program. On the right, I have the source program. And I want to say these programs behave the same, in a sense. Or the left program implements the program on the right. In UC, this means we should be able to translate every attack on the real system or on the real system to an attack on the ideal system. And the way this is formulated is you imagine an adversary attacking your implementation, and you need to come up with a simulator that is derived from this adversary that basically performs the same attack against the source program. We need to talk about what attacks mean. So the real-world attacker is really powerful. It schedules all hosts and all message delivery. It reads all message headers. So if Alice sends a message to Bob, it may not necessarily be able to read the contents of the message, but the attacker knows that Alice sent a message to Bob. It reads all data on semi-honest hosts and fully controls malicious hosts. So this is, before you start execution, you pick a subset of hosts to be semi-honest corrupt, and another subset to be maliciously corrupt. And the adversary takes full control over malicious hosts and partial control over semi-honest hosts. The ideal world attacker, on the other hand, is very weak. There's no scheduling because the source program is fully sequential. We want this because the programmers will be reasoning about the source program, and we want to give them a really simple interface. There are no intermediate messages because there's only one box. There are no corrupted hosts because the source program is idealized. It can't be corrupted. The only thing we do have is the source program communicates with the adversary explicitly, and anytime there's a declassify, it'll send a message to the adversary, and anytime there's an endorse, it'll receive a message from the adversary. And this is basically our way of connecting information flow to something that you do in UC, where you describe the security of an idealized host by explicit communication with the adversary. So if you have a secure channel, anytime it receives a message, it will, let's say, leak the length of the message to the adversary, but it won't leak the actual message to the adversary. And we can derive that communication just from the information flow. So we will be splitting the proof into two halves. We initially start with our ideal world program, where there's only the source program. Then we perform partitioning. So we have these concrete hosts like Alice and Bob, and these idealized hosts like MPC and zero knowledge proofs. This is called a hybrid world. And then finally, we perform cryptographic instantiation, and we do it basically one protocol at a time. So we can instantiate the MPC host with an actual protocol between Alice and Bob, and we can instantiate zero knowledge proof box with communication between Bob and Chuck. And ultimately, we want to do two UC simulations. We want to show that the real world simulates the hybrid world, which simulates the ideal world. The benefits of this two-step approach is that the partitioning step actually doesn't talk about cryptography at all, because we have a uniform representation for all hosts, including concrete ones like Alice and Bob and cryptographic ones. It's fully agnostic to cryptography. When we define simulation, we don't actually have to worry about probability or polynomial runtime. And it's extensible because it does not fix a set of cryptographic protocols. The second step, cryptographic instantiation, is essentially free because we are using proofs from the literature. So let's go through these steps. The first step is correctness of partitioning. What we're trying to do here is we have the hybrid program on the left. We want to show that that UC simulates the ideal program on the right. At a very high level, what we need to do is, given an attack on the hybrid world, we need to translate that to an attack on the ideal world. The way we do it is, well, we have to come up with a simulator that uses the adversary. And our proof technique is that we essentially maintain the entire system on the left. The simulator maintains the entire system on the left in its head. And it's basically trying to trick the adversary into thinking that it's interacting with the distributed program when it's really interacting with the source program. The one issue with this is the simulator is only allowed to see public data, so it can't see all data. So it needs to be able to trick the adversary only using public information. And this is okay because the adversary can only see public information. So the fact that the simulator can see only public information, those kind of match up. And then the way we formalize this is by saying the system in the simulator's head is essentially bisimilar or very strongly related to the actual system on the left up to private data. So they agree on the public stuff, but they can disagree on the private stuff, which doesn't matter for tricking the adversary. We need to have another relation, basically, saying whatever is happening in the simulator's head is basically the split of the source program, or a partitioning of the source program. And the source program only cares about trusted data. So basically, it doesn't hold untrusted data. So this bisimulation is up to untrusted data. So we only say these two things agree on trusted stuff. Step two is instantiating a functionality. So we have Alice and Chuck making calls to an MPC library, and we want to show that this simulates the idealized MPC box that we have. And this step is supposed to be mostly free. The way we go about it is, so we do our proofs in basically a framework that we came up with that uses labeled transition systems. And then we have a notion of simulation. We prove that if there's a simulation in our system, then there's a simulation in simplified universal composability, which is a framework built on top of UC, basically. And that also comes with a proof showing that, if you have an SUC functionality, you can compile that down to UC. There's a translation there. And all the composition basically happens at the UCN, because that's what, when people prove their cryptographic protocols correct, that's what they do. And then for each backend, we need to do this step where we show that, the Viaduct has a notion of what an MPC ideal functionality is. In the cryptographic literature, there's a notion of an MPC ideal functionality. We need to show that these are basically the same. And the way we do it is, there's a pretty strong correspondence between what we generate, or what we call an MPC ideal functionality, and an ideal functionality from the literature. So this step is pretty easy. Okay, so it's all well and good to have UC simulation and say, okay, the output of your compiler, UC simulates the source program. But we are program languages people. We don't really care about UC simulation ultimately. What we would like to say is, the properties that I had in mind for the source program are preserved for the target program. This is where this notion of robust hyperproperty preservation comes in. At a very high level, robust hyperproperty, if your compiler robustly preserves hyperproperties, it means any hyperproperty that your source program had, the output of your compiler will also have. So if you want to say your target programs are non-interfering, you prove non-interference for your source program, and for free you get non-interference for target programs. Or you can basically prove any security property that you care about, and then you'll get it for free for the target program. Of course, we don't want to do another proof, but luckily there's this work by Marco and others that basically makes this observation that UC simulation looks very similar to robust hyperproperty preservation. Like the statements of those two theorems are strikingly similar. And specifically for our notion of simulation at our labeled transition system, we do actually prove that UC simulation implies robust hyperproperty preservation. So, if you prove UC security for your compiler, you basically get one of the strongest notions of correctness you can get for a compiler. Okay, finally, what I want you to take away from this is we're using information flow labels to do protocol selection or host selection and partitioning. And obviously, the proof follows that. So the proof also relies on information flow labels. Using UC allows us to separate the proof for partitioning and cryptographic instantiation, and allows us to use proofs from the cryptographic literature. And finally, UC simulation implies a really strong notion of compiler correctness. Yeah, that's it.
So, questions? I saw.
Hi, how does an attack look from hybrid world simulates ideal world versus an attack in the other layer? I'm a little bit confused on what concrete details, how the attack differs. Suppose there's an attack that's targeting MPC.
Mm-hmm.
How does, at what level, what are the details of those attack at this level versus the other level? Like, is it more concrete in the other level?
Like the next level where we instantiate MPC?
Right.
Basically, what happens at that level is MPC has some code in it, and it has declassifies and endorses, so it's leaking very specific pieces of information. And then, an MPC protocol from the cryptographic literature basically has some notion of, okay, if you give me a circuit, I can execute it correctly, but you will leak this information, or this is the pieces that the adversary can corrupt. And we're trying to show that those two specifications are basically the same.
So the MPC here is a Viaduct program?
Yeah, at this point, the MPC is not that much different from Alice or Bob. It's just some box that communicates with all the other boxes. And you can't really corrupt MPC. I mean, okay, MPC is only corrupted if, let's say, it was MPC between Alice and Bob. If both Alice and Bob are fully malicious, then the MPC box is fully malicious. It means the adversary fully takes over those boxes. You basically remove them from here. And then you can send arbitrary messages. So to ZKP, you can say, oh, MPC box is sending you 5.
So can you actually compose these attacks vertically or no? I mean, you get the proof only if you compose the entire, all the layers, right?
Yeah, so UC simulation is transitive in the sense that if you have a series of UC simulation, you can, if you want to do one big UC simulation, you can chop it up into little simulations. If you're talking about like, oh, I have a system with just Alice and Bob, and I have an attacker against them, I prove something about it, and I want to put it together with some other system that has Chuck and Dave. Are you talking about composing those, or?
Yeah, yeah. I thought I'm just like thinking about just one attack at this level and one attack at the different level, and if you can simulate at the different level. Also here, I'm just wondering if there is a relation between the attack in the second level versus first level, and composing those two.
I mean, the theorem statement is for all attacks, there exists a simulator. And then once you do your proof, you just have a simulation. So you don't prove simulation for a specific attack. You prove simulation for all attacks.
Okay. Okay.
I have a quick remark. Just before Christmas, we updated that Acay version to the fully 50 pages, proving that universal composability is robust hyperparametric preserved compilation, and we even have an Isabel proof. So maybe there's more you can use from that work to simplify your setting. I don't know.
Yeah, I think I had a draft version of that paper.
Excellent. Yeah. Sorry.
I'll look at the full version.
So I think I'm following up on what Anita asked. So I was wondering, so if you have like, so you have these two layers, right? These two levels in your proof. So an attack in the lowest one, does it mean that either you're breaking the, let's say, the MPC protocol itself, or you're breaking, let's say, the way in which, I don't know, Alice and Chuck are using an MPC, right?
Okay, so the attacks you can carry against like a fully, let's say, malicious secure MPC protocol is basically Alice can, you know, whenever you have an input into the MPC box, Alice can send arbitrary data. So the MPC box cannot verify that Alice is sending some sort of like verified data in. But that's not considered an attack. It's like the protocol allows you for Alice to send in anything. And then that exactly matches our notion of what an MPC box is, where if Alice is sending in some data, you know, she can send whatever. The other thing that could happen is if you have corrupted, so let's say if you have a threshold scheme where it says you're running MPC between 5 parties, and if 3 of them are corrupt, then security is off. Basically, our labels will say the same thing. So the label you assign to that MPC box will say, you know, as long as 3 of the parties are honest, this box will act how you want it to act. Otherwise, it will arbitrarily deviate from the protocol.
Okay, thanks.
Yes, I'm curious how you apply UC to your languages, including the source language. When you see it's usually phrased in terms of these Turing machines interacting with each other. So do you have a version of UC that applies to your particular languages?
Yeah, so basically the simplified universal composability model is a lot closer to what we have. I mean, we basically kind of have like an actor model where you have a bunch of parties that are explicitly doing sends and receives to each other. They're not really Turing machines. And that's very different from UC. That's why we're not directly compiling onto UC. ACUC is much closer with some minor differences that we have to worry about. Like it has authenticated channels, but not secret channels, but we're assuming secret channels. So between parties. So there are like some minor differences that we have to handle.
Okay, thank you.
And the SUC thing is not our contribution. It's exists out there.
Someone else? I actually have one,
Okay.
and I wanted to know more about the inference label for the hosts and stuff. It seems to me that the labels actually carry more information than just integrity and confidentiality, right? Is that true, or I'm missing something? Because what stops you from assigning to Bob something that Alice should do?
Oh, so I am alighting a little bit in this example program where endorse and declassify typically requires you to put a label there. So the standard information flow stuff doesn't, if like B has label, little b has label Bob, you couldn't do B equals A because A has label Alice. So that's standard information flow. There's a lattice of labels and
Yeah, so you have not just two levels. You have like a lattice which is richer than like the usual integrity confidentiality lattice, right?
yeah.
Okay.
So the endorse and declassify basically allows you to almost arbitrarily violate standard information flow. Violate is not the right word. Almost arbitrarily deviate from the standard information flow stuff, but we do have a check called non-malleable information flow that basically tells you like these endorse and declassifiers are completely senseless. No one should ever use them, and everything else basically is a valid security policy.
Okay, thank you. So that's a wrap up, I would say. Let's check our screen again.